All right, so remember whenever you're looking at these out of the representative group, that you would just look at the group number to figure out how many valence electrons they have. Some group numbers, the ones once it starts 13O up, you would have to subtract 10 to figure out how many valence electrons, because the most they can have is 8. But over here in group 1 and 2, that is how many valence electrons they have. So we have only one quiz this week, which will be on Thursday. It's on what we covered. We're going to cover today and what we're going to cover tomorrow. Well, after that quiz on Thursday, then we'll kind of do something fun for Thanksgiving. And so on y'all's end, since most of y'all are virtual, then you'll do yours and then take a picture and upload it that way to me. I think it's probably going to be the best way, but we'll talk about that a little bit more. Last day to re-quiz. We have a couple that run out, one on Tuesday, one on Thursday, and then obviously the one that we're not taking until Thursday would go on until we get back from Thanksgiving break. And then my tutorials are listed here as far as what I have for tutorials also. So we're going to be using the notes that we've been working on over chemical bonding. If you look in your classroom, under notes, let's see if I can find it. So they're really fogging up today. If you're virtual, then under notes, rules, Lewis dot, and covalent compounds, you may want to look at that too, especially as we watch a little video over that. All right, so we're going to start with our notes. We're at the top on the back side of the first page. And I think we're right here. So today we're just going to be talking about covalent compounds and drawing Lewis dot structures for those. Is that the top of that? On the back? Yeah, should be there at the top. All right, so some characteristics of a covalent compounds. And remember, when we talk about covalent compounds, that means the electrons are being shared. So the bond length is the distance between the two bonded atoms. And the bond energy is the energy required to break a chemical bond and form neutral isolated atoms. So it's kind of a measure of the strength of the bond. As you increase the bond length, you decrease the strength of the bond. So you would also see a decrease in the bond energy. As that bond gets longer, than the nucleus of the two, or nuclei, I guess, of the two atoms that are part of the bond are farther apart. And so then it becomes a little bit weaker. So the octet rule, we've talked about that before, that elements would like to have 8 valence electrons. That makes them very stable, like a noble gas. So the octet rule is where chemical compounds tend to form, so that each atom, by sharing, gaining, or losing electrons, will end up with their octet. An example of that, we can look at water. So these are the covalent bonds right here between the hydrogen and the oxygen. And so by sharing electrons, one from the oxygen and one from the hydrogen, that oxygen is able to get an octet. It has 2 lone pairs that are its own, and then it has 2 that it's getting whenever it's sharing the electrons here and forming those bonds, and that gives it the 8, their octet. Remember, hydrogen doesn't have to have 8, it only has to have 2, so it is also stable here. So hydrogen is an exception, helium is an exception, boron only has to have 6. There's also something that's called an expanded octet, and you see that with phosphorus and sulfur. They can have what's called an expanded octet, which is whenever they have more than 8 valence electrons. I'm going to kind of mention it to you, but we're not going to really do a lot with it at this level of chemistry. But there is such a thing. We spend a little bit more time with it in AP Chem. And that's not all the exceptions, but kind of the ones that we're going to worry about.
So what were the characteristics of the covalent bonds? B.
The first one was bond length.
Bond length.
Bond length, yes, sir.
Second one.
Bond energy.
Bond length.
You're very welcome. So we're going to be using electron dot notation. It's also called Lewis dot notation to represent the valence electrons that an atom has. And remember, the valence electrons are in the outermost S. I'll read this one in the 3 outermost S and P orbitals. But really, an easier way to do that, instead of writing out the electron configuration, is just look at what group they're in. Because group 1 and 2, they each have either 1 valence electron in there in group 1, or 2 if they're in group 2. And then when we get over to 13 through 18, we subtract 10. So that's probably a lot easier way to do that than having to write out the whole electron configuration. So for example, if I had oxygen, which is in group 6, so it has 6 valence electrons. If I wanted to write its Lewis dot, I'd put its symbol in the middle, and then I'm going to start drawing dots around the outside to represent the valence electrons. So I need to do 6. I put 1 on each side before I would start doubling up, just like we did with our arrows. And that right there would be my, supposed to be 6 dots. That would be my Lewis dot structure for oxygen. Y'all remember doing that in junior high?
Nope.
Y'all did, I promise you.
No, well, we had people who never taught us anything. I didn't really tell them the truth.
Well, it's not too hard. Luckily, it's not too hard. Was that here in Bay City or before you moved?
In Bay City.
Oh, okay. I'm not going to ask you. All right. So here, these are just going from group 1 through group 18, kind of like I did. So sodium is in group 1, so it has 1 valence electron. So that would be its Lewis dot. It doesn't matter what side you put that on. You just need to put 1 on each side before we double up. Magnesium is in group 2, so it has how many valence electrons?
2.
2. So we're going to put 1 on 1 here and 1 there. And that's its Lewis dot. And we could keep on going because boron is group 13. So 13 minus 10 would be 3 valence electrons. 1, 2, 3. Well, that's what I told you. Carbon group 14. 4. My iPad does not like when I do this.
It's like dice.
Yeah, I guess so. That's supposed to be 4 dots, y'all. Nitrogen group 15. 5. So now we can finally double up. So we're going to still put 1 on each side. And now I'll double up. If you would have doubled up and your doubled up one would have been at the bottom instead of the top, that's fine. Oxygen group 16. So 6. 4. And now I'll start doubling up. Halogens, fluorine 7, because it comes from group 17. And finally, my good old noble gas. How many?
8.
8. So I got 2 pairs on each side. Full octet. Very stable. So if we notice nitrogen, I'm just going to kind of rewrite it here. Nitrogen has this pair. It's called a lone pair. And that is not involved in the bonding. Nitrogen will not share those. It's going to keep it to itself. These single electrons can be shared. So nitrogen can form 3 bonds. It can form 3 single bonds, or a double and a single, or a triple. And in fact, nitrogen forms a lot of triple bonds. A lot of compounds with nitrogen end up having triple bonds.
Single electron paired.
Yes, sir.
I guess that's one reason why carbon is so prevalent in organisms, because it can bond on
Exactly.
both sides.
Exactly. It can bond on all sides, and it tends to be in the middle of most compounds because it can bond 4 things around it. Exactly right. That is exactly right. All right. So Lewis structures are used to represent molecules. Dashes or dots can be used to indicate a bond, and then dots themselves are always used to indicate those lone pairs that are non-bonding. So if I have hydrofluoric acid, it's going to be a bond in the middle, and then fluorine still has its 3 lone pairs that it kept to itself. I could have, instead of a line, I could have drawn that as 2 electrons, because remember that line is just representing 2 electrons. Either way would be okay. These electrons here are being shared, and that's what's forming the bond. Hydrogen to hydrogen, just 1 bond in between. No lone pairs, because they only need 2. Diatomic fluorine right here, a bond in the middle, and then each is still going to have its 6 or 3 pairs that it keeps. So by having these 2 that it shares, that's where it gets its octet, because that's 2, 4, 6, 8. And that's how it has its octet, by sharing these 2 electrons that are in the bond. One comes from one fluorine, one comes from the other. So I kind of already mentioned this, the unshared pairs of electrons that are not involved in bonding, they belong exclusively to one atom. There is something called the structural formula that just indicates the kind and number and arrangement of bonds, but not the lone pairs. So that would be where you just simply drew where the bond was, and you didn't draw all that octet or all those lone pairs. They were just assumed to be there. We're going to do it with all the lone pairs, because what we're doing today is drawing Lewis structures, and it kind of helps to see all the lone pairs. All right, so single bonds are covalent bonds produced by sharing 1 pair of electrons. Some elements can form multiple bonds, meaning they share more than one pair. Carbon, nitrogen, oxygen, and sulfur can also do this. So they can form double and triple bonds. So double is when you have sharing of 2 electrons. So we see that in CO2 or carbon dioxide. Carbon is double bound to each oxygen. And then each oxygen still keeps its 2 lone pair. Just like we see it does in water. So if you look at that, the oxygen has an octet because it has its 2 lone pairs, so that's 4. And then this would be considered another 4 in that double bond. The carbon has its octet, and the only way it gets its octet is by all shared. 4 bonds, each bond has 2 electrons, so that's where it gets its 8 electrons or its octet. Whenever I draw those circles, that's not part of the structure. I'm just showing you that to show the octet or the valence electrons. Nitrogen, I kind of mentioned, it likes to form triple bonds. So diatomic nitrogen is nitrogen with a triple bond to another nitrogen. And then each nitrogen keeps that lone pair. That's not part of a bond. All right. All right. So bond length versus bond energy. I talked a little bit about this already. Single bonds are going to have your lowest bond energy, and they're going to be longer. And they are the weakest. Double bonds kind of in the middle, and then your triple bonds are going to be your strongest and also the shortest. So they would have the highest bond energy. If you think of a triple bond, we have 6 electrons making up all those triple bonds or making up that triple bond. So that really pulls in the 2 nuclei of the atoms that are bonding. It kind of shortens it, and then they're able to be attracted to each other more, so that makes it a stronger bond also. Resonance structure is what you see sometimes, and it refers to bonding of molecules or ions that cannot be represented by just a single Lewis structure. And you can tell that it's a resonance structure because it'll have a double arrow. So ozone is 3 oxygen. So if I draw it, that could be one possible way. This oxygen still needs a pair. But we don't know for sure that that double bond is between those 2 oxygen. It could just as easily be between the other 2. So to truly represent it, we would need to draw both with a double arrow in between. And in reality, if you measure the bond angles or the bond lengths, it's probably somewhere in between. It seems like those electrons kind of move between the 2 areas.
On the middle of oxygen symbol in the right one, does it has 3 dots on top?
No, it should only have 2. It looks like 3, but
Yeah.
it's just 2. All right, so I've been drawing all these structures like ozone and the other ones I've drawn, but that's what we're going to do now, work toward learning how to do that. So we're going to start off with a little video, and this that I gave you is your rules for writing Lewis dot structures. And for my virtual students, that's what I refer to. You might want to pull up your rules so you can look at those in case you want to add anything as we watch this video. You can hear me whenever I have this thing frozen. All right, we're going to watch the video that talks about how to write the structures, Lewis dot structures of molecules. So you may want to take notes as you go along on that rule sheet.
At the end of this video, you'll be a pro at drawing the basic Lewis structures. There really are only 5 main steps that you need to know. Let's get started. Step 1, find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try it. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron. But the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6 or 16. It has 6 valence electrons. And when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world around them. Let's try one more, cyanide. For cyanide, we can look on the periodic table again. Carbon has 4 valence electrons, and nitrogen has 5. The trick for this one is, though, it's a negative ion. This negative sign right here tells you that there's going to be 1 extra valence electron. So 4 plus 5 plus 1, 10 valence electrons for the cyanide ion. Step 2, put the least electronegative atom in the center. So how do you know it's the least electronegative atom? Just remember that fluorine is the most electronegative, followed by oxygen. So as you move away from fluorine and oxygen, atoms become less electronegative. That means those atoms will go at the center. Let's see how it works. When I draw the Lewis structure for something like NO2, I can see that nitrogen is further away from fluorine than oxygen. That means when I draw my Lewis structure, I'll put nitrogen at the center and oxygen's on the outside. For something like PCl3, I can see that phosphorus is further away from the fluorine than the chlorine atom. So I'll put phosphorus at the center and the chlorines on the outside, like this. Some Lewis structures, like HCl, only have 2 atoms. In that case, you don't have to worry about it because there's no center. An important note, hydrogen always goes on the outside of Lewis structures. Always. Seriously. Let's look at HCl again. We know it has 8 valence electrons, and we'll put the first 2 in our structure between the H and Cl to form a chemical bond. That's important. By putting those 2 electrons there, we're showing that the hydrogen and the chlorine are chemically bonded now. Step 4, complete the octets on the outside atoms. Octet means 8. For HCl, we have a total of 8 valence electrons, 1 for the hydrogen, 7 for the chlorine. So we've used 2 already to form the chemical bond. For the chlorine, we'll put 4, 6, and then 8. We've used all the valence electrons, and we've completed the octet for chlorine. It has 8 valence electrons. For basic Lewis structures, the big exception is going to be hydrogen. It only needs 2 valence electrons for a full outer shell. So hydrogen has a full outer shell with 2 valence electrons. Chlorine, its octet is full with 8, and we've used only the 8 valence electrons that we have for the HCl molecule. We're done with this structure. There's one more rule that we need to look at. It doesn't apply to HCl, and actually it doesn't apply to a lot of molecules. But what happens when you've used all your valence electrons and you still haven't completed the octets for each atom in the molecule? That's step 5. So sometimes you run out of valence electrons and still have octets. Hey, it happens, right? So in step 5, what we're going to do is if we run out of valence electrons, we'll move some of the valence electrons from the outside to the inside, share them, and form double and triple bonds. Here's how it works. So for O2, oxygen, if I follow all the rules, I count the valence electrons, I have 12. And if I put a bond between the atoms and then fill the outer shell, I end up with a situation where I have an octet for this oxygen. It has 8, but this oxygen only has 6 valence electrons. It doesn't have an octet, and I don't have any more valence electrons. To solve the problem, I can take these valence electrons right here and move them to the center to share them and form a double bond between the two oxygen atoms. I'm still only using 12 valence electrons, but now this oxygen has 2, 4, 6, 8 valence electrons, and this oxygen has 2, 4, 6, 8 valence electrons. So by sharing those valence electrons, I can get the octet on each of the oxygens and still use the 12 valence electrons that I had for the O2 molecule. If I wanted, I could replace these right here with 2 lines to show the double bond, where each line represents a pair of electrons. For Lewis structures like N2, I would even use a triple bond to achieve octets. So how do you get good at drawing Lewis structures? Well, the first thing is know the steps. They're your guide. Second thing is practice. You need lots of practice to get good at this, for it to be second nature. Use the links in this video or go to my website and try more videos. First try it yourself and then watch the video. Pause when you're stuck.
All right. So we're going to look at some of those on your practice. On your set of rules, if you notice, I wrote, it says if any electrons are left over, place them on the central atom. And then in my handwriting, I put this as an expanded octet. Like I said, not something where we're going to really work with, but I want you to know that there are such things. Also, under number 2, I underlined halogens, and hydrogen and halogens are almost always connected to only one atom, which means they're terminal. He mentioned that about hydrogen. Hydrogen can only have one bond, so it's going to have to be on the end. Because of the way the halogens are arranged, they usually are terminal also. They usually also only have one bond. All right, so let's just jump in and look at some examples. And I'm going to do them off of your practice, which is in your Google Classroom. If I can find it. Here, I put it. So too many things opened up by the end of the day. All right. All right, we'll just start with something easy. So the first step to what you do is you see how many total valence electrons you have. Each hydrogen has 1, so 1 plus 1 gives me 2. So I have 2 valence electrons. That's all I have to work with. So this is going to be an easy one. Sorry, y'all. All right, so then my next step is I put my atoms, and here I have 2 hydrogens, so a hydrogen and a hydrogen. And then I put a bond between them. So remember that bond is 2 electrons. So that's all I can do. That's all I have is 2 electrons. So that's my finished structure. And since hydrogens don't need an octet, since they only need 2 electrons to be stable, that would be a good structure. You could draw it like this, or you could draw it like that. It means the same thing. The line means 2 electrons, 1 from each atom. All right, let's look at one that's a little bit more complicated. So oxygen, I have 2 oxygen. Each oxygen has 6 valence electrons, so 6 plus 6 equals 12. So I have 12 electrons to work with. So my next step is I set up my molecule. In this case, I only have 2 oxygen, so it's pretty easy to set up. And I draw a line between them. Then I start giving my atoms an octet. So I'll start on my right side first. It already has 2 electrons, so I'll give it another 2. So that makes 2, 4, 6, 8. So it has a good octet. That's used up 8 of my electrons. So then I'll do 10, 12. So that's 12 electrons. That's all that I have. I can't add any more. Is that a good structure? Do they both have an octet? Nope, that one doesn't have an octet right now. It just has 2, 4, 6. So what happens, I can't just come and add 2 more electrons. But if I look over here, what I'm going to have to do is I'm going to have to go to my other oxygen, which has more electrons, and I'm going to have it donate a pair into that bond. So then it'll be oxygen, double bound to oxygen. And then each will have its 2 lone pair that it will keep. So now if I look at one right here, 2, 4, 6, 8. It has its 8 valence electrons. Not too bad, or what do y'all think? Let's try. Let's see. I'm trying to remember which ones I've been trying today. Okay, let's try. Come down and try hydrosulfuric acid, H2S. All right, so first step, see how many total I have. So I have 2 from the hydrogen and 6 from the sulfur, a total of 8. Then I have to set it up. Sulfur has to be in the middle because the hydrogens can only have 1 bond. So that means they have to be on each side. So now I'm going to put bonds to them. 2, 4. So that used up 4 of my electrons. I have 4 left. My hydrogens don't want any more. So that means I can put a pair here and a pair here. That'll be all my electrons because I have 2 here. 4, 6, 8. Would that be a good structure? That's a good structure, right? Good structure because the hydrogens only need 2 and the sulfur has 8. All right, why don't y'all give this next one, NH3, why don't you give ammonia a try? Oops, do that. See what you can come up for ammonia.
I've got a question.
Yes, sir.
What if one of the 2 elements have two atoms of that specific element, like H2O? Do I add put 2 hydrogen atoms and one oxygen atom in the middle?
Yes, sir.
Okay.
Yeah, hydrogens always have to be on the outside. They couldn't be in the middle.
Okay.
Except you do not, no, I think it has 2, remember, hydrogen only can have 1 bond. And also, you don't, excuse me, you don't want to separate that pair. You want to keep them together. All right, so let's do this one. So nitrogen had 5. Maybe. And hydrogen had 3, so I have a total of 8 to work with. So my nitrogen has to be in the middle. hydrogen, hydrogen, hydrogen. And if you want to put this hydrogen at the top instead of the bottom, that's fine. So that used up 2, 4, 6. That used up 6 of my 8. So I have 2 left. And where do I want those 2 to go? On the nitrogen, right? It's the only thing that isn't stable. Remember, the hydrogens are stable with just 2, but the nitrogen needs 8. Once again, when I draw this circle, it's not part of the structure. But if I look here now, I have 2, 4, 6, and that gives me my final 8. Hydrogen's going to be on the end helium, but helium doesn't. That only would have 1 bond. Well, your halogens, let's do one with the halogen because they usually have 1 bond. They'll have lone pairs around them, but they'll usually have just 1 bond. So what do you want to try? This one, CL4. That one right there. We're going to try this one right here, carbon tetrachloride, CCl4. Carbon had 4 and each halogen has 7. So I got a total of 32 to work with. So would you do me a favor? See that folder I kind of lifted out from lunch? Would you just like move it to the side? Because in my biology class, I have somebody that would probably like to mess with that a little bit. Thank you. Now, as far as which one goes in the center, it says your least electronegative goes in the center. We know fluorine is the most electronegative of everything. So I just look and say, which one is farthest away from fluorine? A carbon. And carbon, like you said, Rodney, earlier, because it has those 4 singles, carbon is almost always in the middle. So I'm going to put a carbon and I'm going to attach my 4 chlorine. Erase that right there. Run out of room. Farthest from and with the weird one would be Jasmine, hydrogen. A lot of time is really far away, but it could never be in the middle. All right, so now I just start filling up my octet for each of these halogens. So give each one 6. 3 lone pair. All right, so now if I look, each halogen has 8 around it. And the carbon, it has 8 around it. All of them are shared, but it still has 8. So if I do my total, 8 times 4 is 32. And that's how many electrons we had to work with. So a halogen, you don't need to write this, but if you think of a halogen, it has 3 lone pairs. And it just has that 1 single. So that's why it is usually a terminal atom, because it only has that 1 single one. So that's why it usually has to be on the ends. There could be some weird exceptions, but really none that we would see at this level. Y'all want to try one more? A little harder?
Which one is N chlorine 3?
Not the. So which one are you going to put in the middle for that one?
Nitrogen.
Nitrogen, exactly. We have, for this one, we had 21 from my halogens. And nitrogen was 5, I should have all that memorized. I don't know why I have to keep on looking. 26, so like you said, I'm gonna put my nitrogen in the middle. Give myself 3 chlorines and start giving them their octet. And if I counted that up right, that should be 24, because 2, 4, 6, 8. 8 times 3 is 24. So I still have how many electrons?
2.
And what needs those 2 electrons?
Nitrogen.
Exactly. And that would be my nitrogen.
I did something similar to the Lewis dot structure when I was little, but with different stuff like numbers.
All right, so we're gonna add one thing to this tomorrow, and then we're gonna work on it a little bit more. And this and this little portion of notes is what you'll see on the quiz on Thursday. We're gonna do ionics, but I think they're a little bit easier. All right, guys, so practice up. I got something in the chat. Just 1 second, please. Aaron, if Cammie isn't working, then you can just write them on a piece of paper. It's not like it's that much to write. It's just some formulas. Another chat. Let me check real quick. All righty. Yeah, just write them on some paper and practice them that way. All right, we'll see y'all virtual tomorrow. We're going to continue on with this and add another step to it. All righty, y'all have a good day. All right, let's get some